Morning, afternoon, or evening. My name is Jordan, and today we'll be talking about collisions. As always, we'll first start with the fundamental principle, and that's the momentum principle, which states that the net force is equal to the derivative of momentum with respect to time. Of course, we've been able to rearrange this equation numerous times to get that force is equal to mass times acceleration. But, as always, it's a key principle, so I have to bring it in. Now that we have our fundamental principle, let's take things a step further. Today we'll be talking about conservation momentum, which states that if there is no net force acting upon an object, the initial momentum will be equal to the final momentum. Okay, before we start the lab experiment, here are the provided masses and the total of the two ping pong balls. Right now we're just going to model a collision. We'll see what type of collision occurs in the tracker video. Here's the tracker video. As you can see, we're modeling 2-point masses, and we also have a scale in the middle left corner denoting our measurement scale for calibration in the video, 13.98 inches. Down below are the standard SI unit conversions of the scale and our initial velocities and initial positions of both balls. I think now is the time that's appropriate to introduce the energy principle once again, which states that the change in the energy of the system is equal to the work surroundings plus Q, which is usually a transfer of energy in and out of the system. In this case, we just only have a change in kinetic energy. You'll see why I'm utilizing this formula in a few. The reasoning behind using the energy principle. As we already know, and whenever we have a conservation of momentum, that means that the change in the momentum in the system is equal to 0. But that also means we're dependent on the final velocity of either the first mass or the second mass, which we can't find, especially in Python code. So we can utilize the energy principle such that we can find what the final velocity of each mass is equal to. That allows us to harness both of the equations you see below. Now, we start on our VPython code. As you can see below, we have the ball's masses, the position vectors, and the initial velocity of the first ball. The initial velocity of the second ball is 0. As you can see in the video, it's standing still until a collision occurs. We also have our time step, which I pulled directly from Tracker in order to maintain accuracy. And we also have the gravitational constant, although it might not be very helpful in this, but it doesn't hurt to have it in here. From the last slide, we have that net force of both objects is just equal to negative mg in the y direction. Although for this model, we're only doing one-dimensional collisions. So again, it won't be useful, but it doesn't hurt to have it. Also, you can see below that we've implemented the momentum principle for ball 1 and ball 2. Now, here's the spicy part. We have to implement conservation of momentum and also be able to detect and handle collision. As you can see, the code here is pretty complicated, but you can see that we've implemented both elastic and perfectly inelastic collisions, just in case we wanted to model something else. In our case, we're only modeling elastic collision equations, so those are the only ones that matter. Below is the computational model of our balls colliding. As you may notice, a bit of the data is off. We're about to address that right now. Now, why is our data a bit inaccurate? Recall that the conservation momentum states that if there's no net force acting on an object, the final momentum is equal to the initial momentum. But in our original video, we did have two net forces acting on the objects, my hand and the force of gravity. My hand cannot distribute a single axis force, allowing the force of gravity to actually affect the ball's velocity and speed in that direction. Now, the big question, was the conservation of momentum held up in the video? Partially. We did have a net force acting on the object, and I could have probably addressed that better by distributing a more even force to ball 1. However, in most real-world situations, there are net forces acting upon objects, ones that are constant net forces, instead of like my hand, which wasn't a constant net force. We could try to address that in our code, but it would be a bit difficult and out of the scope of this course. Before I leave, I would like to say thank you for sticking along on the ride, and see you all in perhaps Physics 2212. Bye.